In this video, we're going to be talking about volumes using the shell method. This first example says, find the volume of the solid formed by rotating the given region around the y-axis. So I've gone ahead and I've kind of mirrored my graph around the y-axis, because that is my axis of rotation. And so far, up to this point, we've really only talked about the disk method and the washer method. And so because there's this gap in the middle, really so far all we have is the washer method to try and find this volume. So I'm going to go ahead and draw my washer. And remember, my washer is this three-dimensional donut-looking thing. And the thickness of my donut I'm going to call delta y. And I need two different values for my washer now. I need my inner radius, which is the distance from my axis of rotation to that first part of my curve. And then my outer radius is the distance from there to there. Now, one thing that you'll notice is this particular curve, y equals sine of x squared, is not a one-to-one function. And if you don't remember what that means, if I drew a horizontal line, notice that that horizontal line would intersect my curve at two different locations. And so what that implies is that this is not a one-to-one function. So what that means is it's going to end up being challenging to calculate my inner and outer radius because they depend on the same curve. So again, to reiterate, we run into difficulty trying to use the washer method because the inner radius and the outer radius depend on the same function that is not one-to-one. So the methods discussed so far for computing volumes of solids depend on our ability to compute cross-sectional areas of the solid. In this section, we're going to develop a new method that can be used when finding the cross-sectional areas that are too difficult or impossible. This new method is called the shell method. First, we need to know what a shell is. A cylindrical shell is a solid enclosed by two right circular cylinders. The volume of a cylindrical shell having inner radius r1, outer radius r2, and height h can be written as. So before I jump into the formula, to the right here we have a graphical depiction of a shell. And essentially, we have a cylinder that has the inner cylinder part, like it's scooped out, and it's hollow. And so the way that we can think about this is we can take a right circular cylinder and subtract a smaller circular cylinder from the larger one. So let's go ahead and call V our volume of our shell. And again, it's going to be equal to the bigger shell or bigger cylinder minus the volume of the smaller cylinder. So I'm going to denote that with V equals V2 minus V1. As a reminder, the volume of a cylinder is equal to the area of its base times the height. And because here we're talking about circular cylinders, the volume of each of these things is equal to pi times the radius squared times h. And here we have what we're calling R2, which is the radius of the larger circular cylinder, and R1, which is the radius of the smaller circular cylinder. So we end up getting this. And from this stage, you might notice that both of these terms have a pi and an h in them. So what I'm going to do now is I'm going to factor out pi, and I'm also going to factor out h from both of those terms. And what I'm left with is radius 2 squared minus radius 1 squared. And inside of those parentheses, you might notice that that is a difference of squares. And so what we can do is we can factor that difference of squares into R2 plus R1 times R2 minus R1, and then we still have the h on the outside. Now, from here, what I'm going to do is I'm going to multiply this expression by 2 and also divide by 2. And why are we doing that? Well, now that I have this fraction, r2 plus r1 divided by 2, that represents the average between those two radii. So this is equal to 2 pi times r2 plus r1 over 2. And I'm just going to move the h over here, and then we have r2 minus r1. And that is equal to 2 pi times the average radius times h represents my height, and then r2 minus r1, that represents the thickness of my shell. And so, kind of going back to the symbolic notation, this is going to be equal to 2 pi times the radius, and r here, if you notice, this going out to the outer circle, or the outer shell, is r2, going to the inner one is r1, and so if I take the average of them, we're just calling that average r. So that's r in this case, and then our height is h, and then our thickness we can call delta r. So this expression here is going to help us with thinking about the shell method, which is going to help us calculate some of these volumes. Below in the left image, we have a continuous function f of x on the closed interval from a to b. If we rotated that region around the y-axis, we can see that the resulting solid would look like in the next two images. So here we have this rotation. This illustrates the shell method. The shell method is different because you are taking the approximating strip parallel to the axis of rotation, unlike the disk and washer methods where your strips were perpendicular. Let's find the volume of the solid generated when the region under f of x from a to b is revolved about the y-axis. So I have some curve here. This curve is y equals f of x, and we're looking at it on the closed interval from a to b. So if I were to take the region bounded by the x-axis, x equals a and x equals b, I'd have this two-dimensional region here, and I'm just going to quickly shade that in. So I have that two-dimensional region, and if I take that region and I revolve it around the y-axis, then I'm going to get some kind of three-dimensional shape. And what I can do is I can create these cylindrical shells to approximate the volume of the three-dimensional shape that we get when we rotate that two-dimensional region around the y-axis. And so notice that we get a more accurate answer as we increase the number of shells. Just like when we were approximating area under the curve, we divide the closed interval from a to b into n subintervals of equal width delta x, and we let x sub I bar be the midpoint of the ith subinterval. Each rectangular strip of base x sub I minus 1 to x sub I and height f of x sub I bar is rotated about the y-axis. So we have created a shell with average radius x sub I bar, height of f of x sub I bar, and thickness delta x. Recall from the previous page, we had that the volume of one of these cylindrical shells was equal to v equals 2 pi times the average radius times the height times the thickness, or another way of putting that is the volume is equal to the circumference times the height times the thickness, because remember when we're thinking about circles, 2 pi times radius is equal to the circumference. So now we have that the volume of the ith shell is 2 pi times x sub I bar times f of x sub I bar times delta x. In order to find the volume of the solid, we rotate each strip around the y-axis and add the volume of all the shells created. So the overall volume is approximately equal to the sum of all of the individual volumes, which is equal to this expression here. And one of my students had a super cool analogy. It's almost like this thing here is a cinnamon roll. And you have these shells that make up the cinnamon roll. And To get an exact answer, what we do is we raise the number of strips. So the volume is equal to this same expression. We are just now taking the limit as n approaches infinity. And what that turns into is this definite integral here. So the volume of a solid like the one in the images at the beginning of this page, obtained by rotating about the y-axis, the region under the curve y equals f of x from a to b, is given by volume equals the definite integral from a to b of 2 pi x times f of x dx, where a is greater than or equal to 0 and a is less than b. To help you remember the above formula, think of a typical shell cut and flattened out like in the figure below. So if I take this three-dimensional shell here, and I cut it and I break it down, this becomes a rectangular prism. And the volume of a rectangular prism is the length times the width times the height. And so we get that the volume is equal to the definite integral from a to b. This thing is the circumference, which if you cut it out and turn it into a rectangular prism is also the width. And then height is f of x, and then our thickness is delta x. Or maybe we can call this the length, and this the width. And then f of x is the height. That probably makes more sense.